students, in this lecture we will continue with our previous discussion on nonlinear optimization models. So, the agenda for this lecture is I will explain what is local and global optima, then I will interpret the meaning of dual values for a nonlinear programming. After that, I have taken a sample problem on nonlinear programming. The problem name is index fund. So, for this problem I am going to formulate in the form of nonlinear problem, then I am going to solve it. Before going to our problem, first we will understand little concept, some concept on local and global optima. Look at this picture. Here there are at the bottom there is a point called local minimum. So, among this minimum, which is the global minimum, this point is the global minimum, and same thing you see there is a local maximum, then there is a global maximum. So, this is an example of the problem of what is the local and global optima. First I will discuss about local optimum in the context of local maximum. A feasible solution is a local optimum if no other feasible solutions with a better objective function value are found in the immediate neighborhood. This is the meaning of your local optimum. So, when we say a problem is local optimum, a solution is local optimum, no other value is better than this value in the neighborhood. For example, the problem which we have discussed, the local optimum corresponds to local maximum. So, this point was our local optimum and the same point also local maximum. So, a point is a local maximum if no other feasible solutions with a larger objective function value are in the immediate neighborhood. That is the meaning of your local maximum. Similarly, for a minimization problem context, a point is a local minimum if no other feasible solutions with a smaller objective function value are in the immediate neighborhood. Look at this point. Suppose there may be some other point, this is local minimum, but when you compare to this is also a local minimum, this also local minimum, because no other values are not in the immediate neighborhood, which is minimum, then it is called local minimum. Then what is the meaning of global optimum in the maximization context? Look at these points are local maximum. This is one local maximum, local maximum, local maximum, local maximum. So, among this local optima, which is maximum, this point is highest point. So, this is called global optimum. Previously we discussed about the local optima, now I am discussing about the global optimum. Nonlinear optimization problems can have multiple local optimal solutions, which means we are concerned with finding the best of the local optimal solutions. Look at this picture, there are multiple local optimum. Among this multiple local optimum, we are going to find out which is the best one. A feasible solution is a global optimum if no other feasible point with a better objective function value are found in the feasible region. Okay. So, you see this is our global optimum, because no other value is better than this. In the case of maximization problem, the global optimum corresponds to a global maximum. A point is global maximum if no other point in the feasible region give a strictly larger objective function value. See, among these different local optimum values, so this is called global optimum because provides strictly larger objective function value. Then what is the global optima for a minimization problem? Look at this picture, there are different minimum, local minimum is available. Among this local minimum, okay, which is the best solutions among this minimum. So, this point is the minimum among these minimum. So, this point is called your global optimum. So, for a minimization problem, a point is a global minimum if no other feasible points with a strictly smaller objective function value are in the feasible region. This point, obviously, a global maximum is also local maximum and global minimum also local minimum. This is also one of your local minimum, but at the same time it is global minimum. Nonlinear problems with multiple local optima are difficult to solve. If there are different local optima is there, for example, like this what we discussed in the previous lecture, this is local maximum, local maximum, local maximum. In that situation, if this kind of problem is difficult to solve, but in many nonlinear applications, a single local optimal solution is also global optimal solution. Sometimes there may be one single solution that also global optimal solution. For such problem, we need to only find a local optimal solution, because that local optimal solution is equal to your global optimal solution. Now, we are going to discuss about some important concepts on nonlinear programming. So, we are going to classify the function into two categories, one is concave and convex. Consider the function f of x comma y minus x square minus y square. The shape of this function is illustrated in this figure. Look at the right hand side, this example is taken from this Anderson et al. A function that is bowl shaped down is called concave function. It is a bowl shaped, but it is down, concave function. The maximum value for this particular function is 0. So, this point is maximum value and the point 0 0 gives the optimal value of 0. So, the point 0 0 is a local maximum, but it is also global maximum, because no point gives us a larger function value. So, if a function is concave function, okay, there the local maximum is equal to global maximum, that is the point, local maximum is equal to global maximum. So, the objective function for the nonlinear problem which we have discussed, the problem is another example of concave function. How can we call it as a concave function? Because look at this shape, minus s square and minus d square. Okay. If the objective function is this form, so then we can call it as this function is concave function. In a concave function context, your local maximum is equal to global maximum. In other words, no values of x or y result in a objective function value greater than 0. The functions that are concave, such as f of x comma y equal to minus x square and minus y square, have a single local maximum, that also a global maximum. So, in a concave function, the local maximum is equal to global maximum. This type of nonlinear problem is relatively easy to maximize. Now, we are going to see another set of functions, that is called convex function. So, in the convex function context, the local minimum is equal to global minimum. What we have seen previously, if the function is concave, the local maximum is equal to global maximum, but if the function is convex, the local minimum is equal to global minimum. I will explain how it is. Let us now consider the another type of function with a single local optimum, that is also global optimum. The function f of x comma y say is equal to x square plus y square. This shape of this function is illustrated in the figure. So, the bowl shaped up and called the convex function. See, this is looking like a bowl upside. Okay. This is a convex function. So, in the convex function, the minimum value for this particular function is 0. Here it is 0 and the point 0 0 gives the minimum value of 0. The point 0 0 in a given figure is a local minimum and a global minimum, because no values of x or y give an objective function value less than 0. So, the learning from the convex function concept is the local minimum is equal to global minimum. Advantage of concave and convex function. As I discussed before, functions that are convex such as have a single local minimum and are relatively easy to minimize, and there is a guarantee that if you recommend a solution that is a local minimum, at the same time that is global minimum also. For a concave function, we can be assured that if our computer software finds a local maximum, it is also global maximum. Similarly, for a convex function, we know that if our computer software find a local minimum, it is a global minimum also. So, concave and convex functions are well behaved and easy to solve. That is why before solving any nonlinear problems, we have to test whether the function is convex or concave. What will happen non-concave and non-convex functions? Some nonlinear functions have multiple local optima. For example, the given figure, you see that there are different optimum values and different maximum values, different minimum values. The figure shows that the graph of the following function f of x comma y equal to s into 1 minus x square e to the power minus x square minus y plus 1 whole square minus 10 x upon 5 minus x cube minus y power 5 e to the power minus x square minus y square minus e to the power minus x square minus y square minus e to the power minus x plus 1 whole square minus y square upon 3. So, the hills and valleys in this graph show that this function has several local maximum and local minimums. So, solving this kind of nonlinear optimization problems is very difficult, and difficult in the sense we can provide a solution, but that is not, there is no guarantee that the solution is global minimum or global maximum. So, it indicates 2 local minimums and 3 local maximums. See that there are 2 local minimum and 1, 2, 3 local maximums. So, one of the local minimum is also global minimum. So, this one, this point. Similarly, one of the local maximum, this is also global maximum. So, from a technical standpoint, functions with the multiple local optima pose a serious challenge for optimization software. So, most nonlinear optimization software methods can get stuck and terminate at a local optimum. Unfortunately, many applications can be nonlinear, and there is a severe penalty for finding local optimum that is not a global optimum. So, developing algorithms capable of finding the global optimum is currently an active research area. But the problem of minimizing a convex quadratic function over a linear constraint set is relatively easy. Why it is easy? Where the local minimum is equal to global minimum, and for problem of this type there is no danger in getting stuck at a local minimum, that is not a global minimum. Similarly, the problem of maximizing a concave quadratic function over a linear constraint set is also relatively easy to solve without getting stuck at a local maximum, that is not the global maximum, because we know if a function is concave function where the local maximum is equal to global maximum. If the function is convex in nature, where the local minimum is equal to global minimum. The next, the interpretation of dual value in the nonlinear problems. So, what is the dual value? If the right hand side constraint, if the right hand side of constraint is increased by 1 unit, what is that corresponding effect on our objective function? So, in the nonlinear programming context also the interpretation is same. So, the interpretation of dual value for nonlinear model is exactly the same as it is for linear programs. However, the nonlinear problems that allowable increase, maybe there may be a constraint, right hand side constraint, the allowable increase and decrease are not usually reported in the software outputs. So, the example of nonlinear programming problem, so constructing an index fund. In the financial applications lecture, we studied portfolio and asset allocation models for a company. Several linear programs were built to model different client attitudes towards risk, okay, client attitudes towards a risk. So, index fund are an extremely popular investment vehicle in the mutual fund industry. The key idea behind an index fund is to construct a portfolio of stocks, mutual funds or other securities that matches as closely as possible the performance of a broad market index such as S&P 500. So, the idea is that we have to construct a portfolio that matches with the index of S&P 500. Assume that a company has substantial number of clients who wish to own a mutual fund portfolio with the characteristics that the portfolio as a whole closely matches the performance of S&P 500 stock index. So, they were saying that these investors that I want to have a portfolio, but that has to match the performance of S&P 500 stock index. So, what percentage of portfolio should be invested in each mutual fund in order to most closely mimic the performance of the entire S&P 500 index. So, what we have to suggest? We have to suggest what percentage of portfolio should be invested, so that will mimic the performance of entire S&P 500 index. So, here this problem we have solved already. See, there are different mutual funds, foreign stock, immediate term fund, large cap growth, large cap value, small cap growth, small cap value. The year 1, year 2, year 3, year 4, year 5 are different scenario. What extra things added in this table is that Standard and Poor 500 return index is given. So, here for the scenario 1 in the index is 25. For year 2 this is a different scenario, the index is 20. So, here index is 8, 30 and minus 10. So, what we are required to do? We have to suggest the portfolio so that it closely matches with the index provided by this S&P company. In the above table, we reproduce all the data which we have discussed in the previous lecture on portfolio, but we have introduced an additional row that gives S&P 500 returns for each planning scenario. So, this was our additional row. Recall that columns shows the actual percentage return that was earned by each mutual fund in that year. So, these 5 columns represent the most likely scenario for the coming year. The variables used in the model is the proportion of portfolio that should be invested in each mutual fund, that was our decision variables. For example, the variable scenario represented by year 1 reflects what happens over the next 12 months. The portfolio return under scenario 1 is R1 equal to 10.06 FS. How we got this 10.06? When you go back, this one 10.06 FS, then 7.64 IB, LG, LV, SG and SV. Similarly, we have repeated, this is return 1, okay, if the scenario 1 is repeated. Similarly, R2, R3, R4, R5 have a return, also have written for other 5 scenarios. So, this slide shows scenario 2, scenario 3, scenario 4 and scenario 5. Next, for each scenario we compute the deviation between the return for the scenario and the S&P 500 return. So, based on the last row of the table, the deviations are, see for example, if the scenario 1 is repeated, the deviation will be R 1 minus 25, R 2 minus 20, R 3 minus 8, R 4 minus 30, R 5 minus 10. So, the objective is for the portfolio returns to match as closely as possible the S&P 500 returns. So, this has to be matched, that means this deviation has to be minimized. To do so, we might try to minimize the sum of deviations given in the above equation. So, we have to sum of the deviation has to be minimized. So, what will happen? Minimize. So, this is a deviation 1, deviation 2, deviation 3, deviation 4, deviation 5 for all 5 scenarios. Unfortunately, we know that if sigma of x minus x bar, when you sum it, it will be 0. So, what will happen if you use the above expression, that is just summation of deviation, the positive and negative deviations will cancel each other. So, a portfolio that has smaller value for expression might actually behave quite differently than the target index. This is the logic, there is a logic behind this. The next lecture we are going to study about mean variance theorem. So, that is sigma of x minus x bar will be 0. So, what you have to do? You have to square this. This logic also behind the variance formula, sigma of x minus x bar whole square divided by n minus 1. So, we have to square this, sigma, the deviation has to be squared, otherwise it will become 0. So, also because we want to get as close to the target return as possible, it makes sense to assign a higher marginal penalty cost for larger deviations than for smaller deviations. Okay. So, what will happen? So, this is called the squared transformation. What is this meaning of the squared transformation? If the deviation is 0.5, when you square it, it will be only 0.25. Suppose the deviation is higher, for example 5. So, when you square it, it will become 25. So, what is the logic behind this is, when you square the deviation, we are giving larger penalty for larger deviation and lesser penalty for the lesser deviation. That is the logic behind squaring the deviation. So, when you square the deviation, then this will become R 1 minus 25 whole square, R 2 minus 20 whole square. This is similar to your least square estimate in a regression. What we used to do there? We have to minimize sum of the square of the error, the same thing. So, what we are doing here, the sum of the square of the error is minimized. So, what is the square here? That is the R 1 minus 25 is the deviation, that is nothing but error. So, we are all the squared error, when you sum it, that has to be minimized. So, if you want to minimize, then what should be the our portfolio strategy? That is what we are going to do. Now, I have brought the complete problem of index fund. So, how we can weigh this is nonlinear? You see this power is 2, power is 2. So, now this problem is a nonlinear problem. What are the constraint? The R 1 is this much, R 2, R 3, and other things, one more constraint, because it is a percentage, the sum of the percentage, sum of the probability should be 1. Okay. So, this is the final complete nonlinear problem that I am going to solve with the help of solver. Now, I am going to solve this nonlinear problem with the help of solver. So, I have brought the screenshot of my formulation of this problem. So, minimize R 1 minus 25 whole square plus R 2 minus 20 whole square, and there are constraint is there. Now, I have formulated, Now, I am going to explain how I have formulated. You see these cells F10 to K10 is the decision variables where we are going to get the answer. Now, look at this E12. E12 is sum product of F10 to K10 and F12 to K12, that is R1, R2, R3, R4, R5. The last cell, that is E17, is sum of the probability. Okay. So, sum of the probability is that F10 to K10 and F17 to K17, because it is 1, it is just sum of the probabilities. Sum product, that will be equal to sum of the probabilities. Now, I am going to data. So, solver. Now, I am going to explain what is our objective function. Objective function is written on E5. Where is E5? Please look at this E5. So, E5 is R1 minus 25 whole square. What is R1 here? E12 is my R1. So, R1 minus 25 whole square plus R2 minus 20 whole square. What is R2? E13. Then E14 minus 8 whole square plus E15 minus 30 whole square plus E16 minus 10 whole square. That is my objective function. Now, when I go to solver, what are the constraint here? The constraint is the sum of the probability should be 1, the changing cell is F10 to K10. So, here I am selecting nonlinear options, instead of simplex I am choosing nonlinear, GRG nonlinear. When I solve it, so I need answer, everything I need. Okay. Okay. Now, I got that in the FS 30% of stock should be invested on FS and 36% of stock should be invested on LV, 22% of stock should be invested on SG and 10.513% should be invested on SV. So, that is the case, the sum of the square of the deviations here 4.42. So, our deviations will be minimized. So, it is at par with index provided by S&P company. Now, I have taken this output in the presentation, there I am going to interpret the result. Yes, here my objective function is 4.42, that is sum of the square of the deviations. So, my constraint, the slack is 0, it is fully satisfied. Okay. So, we are getting this F10 is 30%, 36%, 22% and 10%. The solution for the company is given this figure. The optimal value for the objective function is 4.42, that is the sum of the square of return deviations. The portfolio calls for 30% of funds here, 30% of funds to be invested in the foreign stock FS and 36%, this one, 36% of the funds to be invested in the large cap value and 22.6% of funds to be invested in small cap growth, okay, and 11%, this one, 11% of the funds to be invested in the small cap value, that is why SV equal to 0.10. So, we got this proportions. When you substitute these proportions in the return expression function, we are getting the R1 value is 25, R2 is 18, R3 is 8.97, R4 is 30.22. You see this return, the S&P return given by this company, indexing company. Now, we are finding that if you follow that portfolio strategy, there will be a close match between the index provided by this company and what we are will be getting the return from our own company. So, what we are interpreting, this table shows a comparison of the portfolio return to the S&P 500 return for each scenario. Notice how closely the portfolio returns match the S&P 500 returns. So, based on the historical data, the portfolio with this mix closely match the return of S&P 500 stock index. In this lecture, I have explained the concept of convex and concave function and its advantage. By using the concept of convex and concave function, I explained the local optima and global optima. What is that? If the function is concave function, the local maximum is equal to global maximum. If the function is convex function, the local minimum is equal to global minimum. Then I have explained the meaning of dual value in the nonlinear problem context. After that, I have taken a sample problem for constructing an index fund. So, that problem is nonlinear problem that I have solved using solver, then I have interpreted the result. The next class, we are going to take an interesting problem, that is Markowitz portfolio models. We will see you in the next class. Thank you.